Welcome to the third video in a series of 4 about inverse trigonometric functions. Here we're going to look at composite trigonometric functions. But before we get into that, let's talk more generally about what composite functions are. Putting trigonometry aside, just for a moment, suppose we had two functions f and g as shown here. If we were asked for the composite of f composed with g at 5, also known as f of g of 5, this would essentially amount to plugging one function value into another. So the first thing I would have to do here is to compute g of 5. In other words, I've got to start by working out the inside function in the composite. G of 5 is easy to work out based on the formula they gave us. G of 5 is 7. And so I can replace g of 5 with 7, thereby working out the first, or the inside function, before going to the second, or outer function. And now, f of 7 is just 7 squared, and 7 squared is 49. Now back to the world of trigonometry. So here we're going to look at this composition of functions. In order to work this out, or simplify it, I've first got to work out the inner function. So to do that, I've got to find the inverse cosine of radical 3 over 2. Let's ignore the tangent for now and just focus on the inside function. As you recall from a previous video, hopefully, inverse cosine of a number means that I have to find an arc length between 0 and pi whose cosine equals that number. Now in order to find this, one has to have a good command of the unit circle, because there's no math procedure that you can follow here. Eventually you'll discover by guess and check that of all the angles whose cosine is radical 3 over 2, pi over 6 is the only one between 0 and pi that will make this statement true. Now many students get frustrated here because they think that the pi over 6 came from some calculation, or that there's some method that you could use to find that. But honestly, there isn't anything that you can do other than have a great command of the unit circle, and just know that the cosine of pi over 6 is radical 3 over 2. And if it doesn't pop into your head, no big deal. You just have to do trial and error and do the cosine of everything you can think of on the unit circle until you accidentally get radical 3 over 2. But it is a guessing game, and the better you are at the unit circle, the less time you'll spend figuring out that pi over 6 goes there. So back to our main problem on the left, what we've done now is we've found a value for the inner, or first, of the composition of these two functions. In other words, I've found that the inverse cosine of radical 3 over 2 is pi over 6. That had nothing to do with the tangent. That was just me working out the inner function in this composition. And now, what remains to do is to compute the outer function, or the tangent. So applying tangent to pi over 6, once again, requires in-depth knowledge of the unit circle. To do the tangent of pi over 6, although the work isn't shown here, you'd have to find the sine of pi over 6, the cosine of pi over 6, and then divide sine divided by cosine. While none of that is shown, the end result becomes radical 3 over 3. That's the answer to this composition of functions. Now let's look at our second of 3 examples, shown here. Again, let's start this problem by examining the inside of the two-function composition here. Let's ignore the inverse sign, or our second function on the outside. We can simplify the sine of 5 pi over 6 by just knowing something about the unit circle. And you should know enough about the unit circle, hopefully by now, to know that that is 1/2. So I've worked out the first of the two functions in this composition. Now I have to apply the second function, or the inverse sine. So the inverse sine of a half means, by definition, to find an arc length between negative pi over 2 and pi over 2, such that the sine of that arc length is a half. In other words, the sine of what would equal a half? Well, if you know enough about the unit circle and you're comfortable with that, you'll eventually discover that it's pi over 6. Now, there are many arc lengths whose sines are a half, but the only one that's between negative pi over 2 and pi over 2 is pi over 6. Many students get confused here because they think that I got pi over 6 by some kind of calculation or procedure, but truthfully, that's not how it works. I just knew enough about the unit circle to know that the sine of pi over 6 is a half. And if you don't, if you're not that comfortable with the unit circle, just start taking the sine of all kinds of different values of your favorite 16 points on the unit circle, and eventually you'll stumble across, oh yes, the sine of pi over 6 is a half. Well, now that I know that, I've answered the inverse sine of a half, and thereby answered the original problem. And lastly, let's do this composition of functions. So, as we described earlier, we're going to focus on the inside, or the first of the two functions of this composition. Let's ignore the cosine for just a moment and see what we can make out of inverse sine of negative 2/3. Well, inverse sine of negative 2/3 represents the unique arc length between negative pi over 2 and pi over 2, such that the sine of that arc length is negative 2/3. Well, let's examine that on the unit circle. If the sine of something is negative 2/3, then that something must have a y-coordinate of negative 2/3. After all, the sine is the y-coordinate on the unit circle. Well, there are 2 points on the unit circle that have a y-coordinate of negative 2/3. But I'm not interested in the one on the left, because the one on the left cannot be between negative pi over 2 and pi over 2. So I'm more interested in the remaining point as my terminal point for this arc length. So the arc in question must appear there. Let's call this point P. Now we're in a unique position here that we were not in either of the previous two problems. Why? Well, because P is not one of our favorite 16 points on the unit circle. There are no points, none of our 16 favorites have a y-coordinate of negative 2/3. We know that by just memorizing all 16 points. And therefore, the inverse sine of negative 2/3 is not computable by any of the methods that we've seen in these videos, because everything that we've done up until this point corresponds to one of our favorite 16 points. So it turns out you could compute the inverse sine of negative 2/3 and get a decimal approximation on a calculator. That's not what we're interested in here. We're interested in seeing if we can simplify the original problem without a calculator. So how am I going to go about computing the inverse sine of negative 2/3? You may see it in red at the top. How am I going to go about computing that if it doesn't correspond to one of my favorite 16 points on the unit circle? Well, in isolation, I wouldn't without a calculator. But it turns out, and here's the funny thing about this problem, even though I cannot compute the thing in red as an exact value, I cannot find the exact value of inverse sine of negative 2/3 without a calculator, I can still find the cosine of that unfindable arc length, because that arc length is represented by the red arc at the bottom of the screen. Now, just to give it a name and to stop calling it the arc at the bottom of the screen, let's call it theta. Don't let Greek letters freak you out. They're just like any other letter. And if we call that arc length theta, or theta, let theta equal negative that arc length, I should say, then the problem at the top of the screen is really no different than just computing the cosine of theta. And while I can't get an exact value for theta, again because p is not one of our 16 favorite points, it doesn't matter. Because even without finding theta itself, I can still find the cosine of theta. After all, the cosine of theta is just the cosine of the arc that terminates at p, otherwise known as the x-coordinate of point p. So I can find the cosine of theta without ever finding theta itself. So now the question becomes, how am I going to find the x-coordinate of p? Well, I can use the equation for the unit circle. I know the y-coordinate after all, that's negative 2/3. And by just doing some very basic algebra, I can get down to two possible values for x, plus or minus radical 5/9. But of course, p has a positive x-coordinate. You can see that just by looking at it. And therefore, I can eliminate the plus or minus and just replace it with plus. And then after a brief simplification, distributing the radical to the fraction and assuming and knowing that radical 9 is 3, I now know the x-coordinate of point P, and that's what I was trying to find to solve the original problem. And so the original problem simplifies to radical 5/3. And notice one more time that while I never found the actual value of theta, I was still able to find the cosine of theta, as shown in this problem. And that completes the third of 4 videos in this series.